All right, welcome back to another episode of Science with Surbeck. Today what we're going to be talking about is how temperature affects rate. Now before we get into the details of these notes, there's a couple of objectives that I have for you during this video. Objective number 1, explain the concept of activation energy and how it relates to the variation of reaction rate with temperature. Objective number 2, determine the activation energy for a reaction from a knowledge of how the rate constant varies with temperatures, also known as the Arrhenius equation. And objective number 3, use the collision model of chemical reactions to explain how reactions occur at the molecular level. So we start out here with the collision model. And the collision model is defined as a model based on the kinetic molecular theory, which explains how the rates of reactions are affected by concentration and temperature. Now, for a chemical reaction to occur, they're going to require two things. 1, collisions between molecules. And 2, there must be proper orientation between colliding molecules. So to help emphasize what we mean by these two things need to occur for a reaction to happen, I'm going to draw a little bit of a picture here. So let's say we have this particular molecule. We'll just make it a green molecule. And it's trying to react with this orange and blue molecule. And so we'll draw the blue molecule here. And we'll draw on the other side the orange molecule. So this is before the reaction occurs. Now, remember from the kinetic molecular theory that all molecules are in motion. So I'm going to draw a couple of things or write down a couple of things. Number 1, this is before the collision. And then number 2, if a reaction is going to occur, these molecules need to be able to run into each other. So I'm just going to draw arrows that show these molecules are going to smack into each other. Now, during the collision, we'll draw this next picture here where our green molecule has ran into the orange and blue molecule. And if a reaction is going to occur, we have to have this collision and they have to be orientated in the right direction. So let me draw this, and again we will explain everything that's happening. And I kind of drew them oblong here in shape because the molecules have smacked into each other. So this is during the collision. And if this collision has proper speed and orientation, so we have the collision and there is, let's say there is enough speed and the molecules are orientated correctly. If these two things happen, then we can get that chemical reaction to occur. So again, if we have a collision with enough speed and these molecules are orientated properly, so let's say we had that proper orientation, what we'll get now is this. We'll get that reaction to happen, and to show this reaction from happening, or to show that it is happening here, we will trade places with that green and blue molecule here, okay? So we now have our aftermath of our collision. So this collision resulted in enough speed and it was properly orientated, or I should have added the orientation is correct, we get a chemical reaction to occur after the collision of molecules. So that's what the collision model is saying is, hey, we have to have these molecules smack each other or have collisions with proper speed, and they have to be orientated correctly. So our example here, maybe if this green molecule smacked the orange molecule, maybe the reaction doesn't happen because there is no proper orientation. Or if these molecules are moving slow, the reaction doesn't happen because there has to be enough speed, enough kinetic energy to jar these molecules loose and produce the aftermath or the products. So now that we have this idea in mind about the collision model, we can move on to a topic known as the activation energy. Okay, so activation energy is defined as the minimum energy required to initiate a chemical reaction. In other words, what this is saying is, do the molecules, when they collide together, do they have enough speed to have this minimum threshold for energy? And yes, they're also, along with this proper speed or enough speed, those molecules still need to be orientated in that correct direction. So activation energy has the symbol of E with a subscript A. Now, depending on what type of reaction we're dealing with, the activation energy, or E sub A, will vary with each and every reaction. Now, the key takeaway here on this business of activation energy is that molecules must possess a minimum amount of energy to be able to react. Now, how we identify the activation energy is through what we have as a reaction diagram. So a reaction diagram is going to have a few characteristics. Number one, it's going to look very, very similar to a graph, and it's going to have a couple things in this. Number one, on this y-axis, this is going to be the potential energy of those chemicals involved in the reaction. Number two, on this x-axis, this is going to be known as the reaction progress. So what is happening as the reaction goes from products to reactants. Now, how we orientate this is as follows. So if we have our starting stuff right here, we would have something that looked like this. Now, the starting thing on the left-hand side, this flat line here, this is our reactants. And this finish line here, or this bottom portion here, are the products. And what we have at the top, or between the reactants and the top, so right here, the arrow I'm just going to draw, this right here is our activation energy. So this energy right here, this is the minimum amount of energy that a reaction, and this is just a generic reaction, but this is the minimum amount of reaction energy that must happen for a reaction to occur. Now, if a reaction reaches that minimum amount of energy, what happens here is this. So right at the peak, the reaction has reached the amount of activation energy. We then begin to go through a transition state. And so in a transition state, the reactants are now becoming products. Now, one other thing to talk about here is the difference in height between the reactants and products. So this right here, this second arrow that I'm drawing below is the enthalpy change that occurs during a reaction. Now, if the products are lower than the reactants, by the end of the reaction is exothermic, or in this case, it would give off heat. Now, if the products were way up here where that activation energy is, that flat line, the products would have to take in heat, or the reaction would take in heat, and it would become endothermic. So depending on where the products are in comparison to where the reactants will dictate or determine whether the reaction is endo or exothermic. So there's a lot of information contained in this particular diagram. Now let's go through some examples here and talk about here what is happening as we go through activation energy. And what we're going to do is we're going to do an example. So our example here is this. We're going to look at these reaction diagrams, and they say they have these energy profiles. Well, again, that's everything that we've discussed here. We want to know, okay, what reaction goes from the slowest to the fastest? Well, what we need to know first is, well, how do I determine the slowest versus the fastest? So the slowest reaction is going to have the greatest activation energy. So slowest reaction means you have the greatest activation energy. And on the flip side here, the fastest reaction is going to have the least amount of activation energy. So again, fastest reaction equals the least, or the smallest, that's probably a better word, smallest activation energy. Okay? Slowest reaction equals the greatest activation energy. Fastest reaction equals the smallest activation energy. So a couple of things here is this. The activation energy, remember, was from that starting line all the way up to that transition state. So I'm just going to mark that as our EA on each of these three diagrams. Okay? So again, the slowest reaction is going to have the greatest activation energy. So our reaction with the greatest amount of activation energy is reaction number 2. So reaction number 2 is going to be the slowest, and then the next amount of activation energy is reaction number 3. And then that leaves us reaction number 1. So a couple of things. Reaction 2 is the slowest because it has the greatest activation energy, and reaction number 1 is the fastest because it has the smallest activation energy. Now, before we leave, I want to go one step further that this question doesn't ask. I want to talk about our exo and endothermic reactions. So remember this statement. If the products are lower in energy than the reactants, we have an exothermic reaction. So right here, see how the products at the very bottom are lower in energy than our reactants. This would give us a delta H value that is negative, and this would result in an exothermic reaction. Now we move over here to this next reaction, and again, the products are lower than the reactants in terms of energy, so that again means our delta H is negative, and this would produce an exothermic reaction. Okay, now we get over here and check this out. The products are higher in energy than the reactants. So in this case here, delta H is positive, which means we have an endothermic reaction. Okay, so we have that in mind. We have the collision model, the activation energy, the minimum amount of energy that is required, and we can also identify some things off a reaction mechanism diagram. So now we can move over to our business here of how does temperature affect rate. We still haven't got there, and we do this by talking about the Arrhenius equation. So a couple things about the Arrhenius equation. Number one, the scientist by the name of Arrhenius discovered that most reaction rate data is obeyed in an equation based on the following three factors. The first factor is that the value depends on the number of collisions per unit time. The second factor is the fraction of collisions that occur with the correct orientation. And the third factor was the fraction of colliding molecules that have an energy that is equal to or greater than the activation energy. All right, so this is all fine and dandy here, but Arrhenius actually had a formula for his equation. And that formula here, there's going to be a couple terms we'll have to discuss, but that K, that rate constant, is equal to A, which we'll talk about here in a second, all e to the power of negative activation energy over RT. Okay, so K is the rate constant. A, this is a new term here, but A is called the frequency factor. So the frequency that this A was measuring was how many times or how many molecules had the proper speed and proper orientation for a reaction to happen. And that was Arrhenius's contribution here to this formula, is he determined that frequency factor for most reactions, or he's able to develop that term that we use today. Now, this E button, or this E value, is very, very important. It is the inverse natural log. Everyone see that on the calculator? You have E to the power button. That is what that is saying with that. So don't confuse that with a term. But our EA, we've seen this before, is our activation energy. And then R is our gas constant. And that has a value of 8.314 joules per Kelvin mole. Now, our last thing that we have to talk about is our T for temperature, and that's going to be in Kelvin. Now, this formula here that we have listed right now is not very useful to us because we want to have a comparison between our temperatures, okay? So what I'm going to do is I'm going to write this next equation on a blank sheet of paper. Okay, so we have the Arrhenius equation here. And so like I said before, this isn't helpful because, hey, we want to see the effect of changing our temperature on rate. That's been the whole objective of this entire unit. So what we're going to do, we're going to manipulate the Arrhenius equation to make it a little bit more useful for us. And now I don't expect you to be able to perform this, but I'm going to show you how we get to that formula that we want. So the first thing that we're going to do is we're going to multiply each side by natural log, okay? And so when we do this, we get natural log of k, and then we have a unique property here. What happens here, because a and this inverse natural log are attached via multiplication, and we're using natural log, the rules of natural log say that we can do the following. We can say, hey, we have natural log a plus the natural log of e to the power of the activation energy over RT. Okay, so that's really, really helpful. And now what we can do is this. We are taking the natural log times, if you look here on your calculator, times the inverse natural log. Well, anything times its inverse is 1. So we can rewrite this equation to be the natural log of k equals the natural log a plus the negative activation energy over RT. And remember, we got rid of the natural log and inverse natural log because one is the inverse of the other, and that allows us to just obtain this value here. Now what we can do, I'm just going to rearrange this, and I'm going to have this formula here, natural log of k equals the negative EA over RT plus the natural log of A. Now this is a lot nicer equation, except for the fact that this is only for one temperature. So I want to make that clear here. Only for one temp. I'm going to abbreviate that. Only for one temp. We want to do some comparison between the reaction at one temperature and the reaction at a different temperature. So we want to compare two temps. So what we can do is this. For temperature 1, so I'm going to call this temp 1. For temperature 1, we can say we have the natural log of K1 equal to the activation energy over RT, and that is going to be temperature 1 plus natural log of A. Now for temp 2, we can do the same exact thing, but now we're going to have the natural log of K2 equals the activation energy over R times the temperature 2. So that's our difference here, plus the natural log of A. So now what we're going to do is this. To be able to compare this, we're going to subtract the stuff from temp 2 from temp 1. So to help us out here, we're going to subtract natural log of K2 equals the negative activation energy R times temperature 2 plus the natural log of A. So what happens when we subtract this is as follows. We would get the natural log of K1 minus the natural log of K2, all set equal to the negative EA of R times T1 plus the natural log of A minus negative EA over R times the temperature 2 plus the natural log of A. Well, what we can do is this. We can, if you look closely, do a couple things. One, we're dealing with natural logs. So a natural log minus a natural log, what you can do, you can consolidate this because of the rules of natural logs. You can say natural log of K1 divided by K2 equals the activation energy over R. See how both of these have activation energy over R? So we can say, hey, this is going to be the activation energy over R, and the signs would cancel out because we're going to do the following. We still have the temperatures to worry about. So we can say 1 over T2 minus 1 over T1. And because we reverse where temperatures 1 and 2 are, that is why we get rid of that negative sign in front of that activation energy. Now, our last thing we actually don't include, because think about this. We have a positive natural log A minus natural log A. So we're subtracting one thing from itself. Well, if you do that, you take it away, you make it 0. So in our formula here, we are not going to include this. But again, because of the powers of natural log, we can obtain this value that is a lot more useful for us when we compare two temperatures. So this is one formula that utilizes the Arrhenius equation and the powers of natural log to be able to compare what happens with the activation energy from one temperature to another. So let's go ahead, let's apply this business here to be able to do this in an example problem. Okay, so our example problem here, it says, hey, calculate the activation energy for the following reaction. We have two experiments which are conducted at different temperatures, and we have the given rate constants. Okay, so from what we just did on the previous page, we're going to utilize that formula. So the natural log of K1 over K2 is equal to the activation energy over R times our 1 over our temperature 2 minus 1 over temperature 1. So what we're going to do is just plug these values into our equation. So we're going to get the natural log of K1, which is 4.5 times 10 to the third inverse seconds, all divided by the rate constant of 1.0 times 10 to the fourth inverse seconds. And we're going to set that equal to our EA. We don't know what the EA, because the problem is saying, hey, go find the activation energy. All over our R. And our R, remember, is 8.314 joules per Kelvin mole. So we have 8.314 joules per Kelvin mole. Now, we multiply that by 1 over the second temperature, so 284 Kelvin, minus 1 over the first temperature, which is 274 Kelvin. Okay, so all we're going to do is plug these values into our calculator. So what I'm going to do first, I'm going to take care of this natural log business. So I'm going to hit natural log, another set of parentheses, so 4.5 times 10 to the third divided by another set of parentheses, 1.0 times 10 to the fourth, two set of parentheses. I get a value of negative 0.799. Okay, so negative 0.799 is equal to our business here. So what I'm going to do is two things. Number one, I'm going to knock out 1 over 284 minus 1 over 274, and I'm going to press enter. Now that is just this business here. What I'm going to do is I'm going to cross multiply it with that 8.314. So I'm just going to take times 8.314, I press enter. I don't want to write all that stuff down, so I'm going to put it into scientific notation. I am going to get activation energy times, when I do all of that business here, times negative 1.07 times 10 to the negative third. So this is going to be negative 1.07 times 10 to the negative third. And the unit, because we use temperature here, the unit is going to become joule per moles. Now, we need to get activation energy by itself. So what we end up doing is dividing everything that is attached to our activation energy. And so all we're going to do here is we're going to divide both sides by negative 1.07 times 10 to the negative third joules per mole on each side, okay? And I'm sorry, this would be, I should have reversed that. This would be moles per J. And I'll show you why I did that here in just a second. That should be moles per J. It's because if you look here, this is on bottom. So when we flip this all around, this is why this is going to happen. So again, negative 1.07 times 10 to the negative third moles per J. Okay, very important that we have that there, because when we divide moles divided by J, we're actually going to flip the unit and it's going to become joules per mole. So what we're going to do here, we're going to take negative 0.799 and we're going to divide it by negative, very important, 1.07 times 10 to the negative third power. We press enter. We're going to round to 3 significant digits. Well, you could really round to 2 significant digits. So you get a value in our calculator of 747 joules per mole is our activation energy, or our EA. Now, like I said, because of sig figs, this would actually round to 750. So if you want to put sig figs down here, this would actually be 750 joules per mole as our EA, or our activation energy. All right, so this is a very important part about chemical kinetics, and it really explains a lot about why reactions happen, or why it takes some amount of energy for a reaction to start. And all of this here leads up to this activation energy and how it's affected, or how it can be transitioned from one temperature to another. I hope you have enjoyed this particular episode dealing with a little bit more detail on kinetics. And if you haven't already, make sure you subscribe.